Today we're moving into probability models. So we had an introduction yesterday on some of the key terms for probability and how to calculate probability. We're going to use several different sort of representations of how we can consider probabilities. So we have four of them we're going to look at today. First is the ordered list, which we looked at yesterday. Tree diagrams we'll look at in more detail today. Area models, which is a new one, we haven't seen that one yet, and then finally two-way tables, which we're just going to introduce but not get into them in too much depth because we will talk about them pretty extensively later. So the first one, make an ordered list. So you have a boy who has 3 shirts to choose from, red, blue, and green, and then 2 different pairs of pants, white or black. So how many different combinations of shirts and pants could he wear? What is the probability that he randomly chooses a blue shirt and white pants? Okay, so you need to make a little list to figure out all the different possibilities. So we start by listing the shirts. We have 3 different possibilities, red, blue, and green. And then we have 2 possibilities of shirts, black, which I call with a K to distinguish from blue with a B, and white. Okay, so now we're going to start listing our possibilities. Well, we could go red with the black, red with the white. We could go blue with the black and blue with the white, or we could go green with the black and green with the white. So quickly you figure out that there are 6 different combinations that you could try. Incidentally, you can come to that number pretty quickly if you just think about, okay, if you have 2 different combinations, if we have 3 in the one case and 2 in the other, just take 3 times 2 and that's going to give you 6. We'll look at counting when you have large numbers of combinations like this and learn some of the rules at that time, but basically you're just taking the number of choices for each choice and then multiplying them together. Okay, so 6 different combinations that you could use. So what's the probability that he randomly chooses a blue shirt and white pants? Okay, so there's a blue shirt and white pants, and that's only one of the 6 choices, so you'd say the probability is 1 in 6. Okay, next one. Tree diagrams. So when you're looking at a tree diagram, it helps you consider probabilities, and you can, again, they can be either dependent or independent when you're doing tree diagrams. But for pretty complex scenarios, tree diagrams are really helpful. So in this scenario, if you look at the 2 spinners, we have one where if you spun a little arrow around it, it would come to a stop. It might come to a stop right here in the eye section. Well, the eye represents half of the area of the entire circle. And if you look at the A, it looks like that's about 2/3 of 1/2, or about 2/6 or 1/3 of the entire circle. So that's going to be 1/3, and then the U looks like it represents about 1/6 of the entire circle. Again, if you could remember our sector types of discussion, we're trying to figure out proportions of the entire circle. So if we break it up, we could figure out that the I represents 3/6 of the whole thing, the A represents 2/6, and the U represents 1/6. By the same argument, you could look at the second spinner and realize that the T represents 1/4 of the whole pie, and the false represents 3/4 of it. Okay, so here's the situation. A tree diagram used even if there are more than 2 probabilistic situations. The events can be independent or not. So here they go. Let's say you do the first spinner and you come up with either an I, a U, or an A. And so we list those possibilities here, I, A, and U. Those are the 3 different choices you could get by spinning it, by spinning the spinner. Now, if we had more chunks of pie, like let's say there was 5 different size chunks, then our tree diagram could have 5 different possibilities. And then what we do is we list the probability of one of those being selected. So in the case of the I, it's 1/2. In the case of the A, it's 1/3. In the case of the U, it's 1/6 of the time. Okay, so you spin the first spinner, and then after you spin the first spinner, you spin the next spinner. And you know that you have different possibilities for that one because it's a different kind of spinner. So if you go with that spinner, then you're going to have 1/4 possibility of T and 3/4 possibility of false. So you'll add on some new branches to your tree. So if you're at the I, let's say you first spun an I, well then you're going to spin the second spinner. 1/4 of the time you're going to get a T, 3/4 of the time the F. And that's going to be true for each of the branches. So if you've selected an A the first spin, you're going to have those same 1/4, 3/4 possibility after that. So to get the final probabilities, the trick is to multiply the different branches. So 1/2 times 1/4 means that 1/8 of the time you're going to get the I-T combination. So first the I, then the T. And 3/8 of the time, because you multiply 1/2 times 3/4, you're going to get 3/8 of the time you're going to get an IF combination, and so forth. So as you work your way down the tree and you multiply these different terms, 1/3 times 1/4 gives you 1/12 of the time. It's going to give you an AT, and then AF is 1/3 times 3/4 or 1/4 of the time, etc. Now, if you've done it right, then all of these probabilities should add up to give you a fraction of exactly 1. If you want to trace one particular route, then you say, well, what's the fraction? It says, for example, the probability of spinning a U and then a T. Well, you just trace the UT path. That's going to be 1/6 times 1/4, which is 1/24. So that would be 1/24 of the total probabilities. Okay, here's another one. We got a mouse. There's a maze, and the mouse needs to get into either room A or room B. And the deal is that every time Romeo, that's the name of the mouse, reaches a split in the maze, he is equally likely to choose any of the 3 paths in front of him, or 2 paths if there's 2. But whenever there's a split, he's going to equally choose between those. So it says make a tree diagram and calculate the probability that Romeo will end up in each room. So what's the probability he'll end up in A? What's the probability he'll end up in B? So before you start working, you might just pause and look at it and think about which one you think is going to get the most highest probability. Okay, so we're going to work a tree diagram. So here it is. So we say, all right, as he goes to the first branch, he's going to have equal probabilities of splitting up. So he's going to go to the top branch, the middle branch, or the bottom branch, and equally probable that he would go 1/3 of the time he's going to go top, 1/3 of the time he's going to go middle, 1/3 of the time he's going to go bottom. Now, if he goes top, then there are 1, 2, 3 branches that he could take in that direction, and 2/3 of the time he's going to end up in room B. So I combined the 2 different branches into B into 1 to say that, okay, once he gets to this junction right here, he's going to split up 2 of the 3 chances he's going to end up in B, and 1 he's going to end up in A. So I branch off right here to show those 2 possibilities. If he goes down the middle track, that's definitely going to take him to A all the time. So you're just going to say that's going to go there A 100% of the time. And then if he goes down below to this branch, well, half the time he's going to end up in A, and half the time he's going to end up in B. So now we can trace and calculate the total probabilities for every single branch. And all we do is we just multiply them out. So 1/3 times 2/3 is going to give us 2/9. 1/3 times 1/3 gives you 1/9. 1/3 times 1, for that just straight shot down the middle, is just 1/3. And so forth until we get them all multiplied out. And now that we have them multiplied out, we can combine the probabilities of the different branches. So what is the sum total of all the probabilities that it's going to go into A? What's the sum total of the probabilities that it's going to go into B? So you say the probability of A is just 1/9 plus 1/3 plus 1/6, which is 11/18. What's the probability of B? Well, that's going to be adding 2/9 and 1/6. So combine those under the same denominator, you get 7/18. And yes, indeed, those 2 probabilities, 11/18 and 7/18, do add up to 18/18 or 1. So all the probabilities when you're doing a tree diagram should add up to give you the value of 1. If you've done that, it should. If you've done it right, that's what will happen. Okay, so here is a new one, though. This is an area model, and these are very confusing. So one way to represent a sample space that has the outcomes are not equally likely is by using an area model. In this type of area model, we're going to say that use the whole. It's like a percentage-based model. So we're going to say use the whole box and assume the whole box is equivalent to an area of 1, and then we're going to divide it into fractions. So if we know that a quarter of the U.S. population can bend their thumbs back, then the column representing disability should take only 1/4 the square. So you divide shade in 1/4 of the whole square, because that's going to represent the quarter of the population that can bend their thumbs back. So it says, and how should the diagram be altered to show that 7/10 of the U.S. can roll their tongues? So we're going to combine by overlaying what would happen with people who roll their tongues. Well, 7/10. So 7/10, we got to shade in a section of the graph that represents about 7/10. So we'd say that 7/10 of the people can roll their tongues, and 3/10 of the people cannot roll their tongues. And I try to make the size of the shaded area about 7/10 of the square and 3/10 of the square. So it looks something like this. And then you want to say, well, what is the probability that you can both bend your thumb and roll your tongue? Well, that's going to be the net shaded area inside the yes column for each. So it's going to be 0.7 times 0.25, and that's going to give you 0.175. So 17.5% chance that you could do both, roll your tongue and bend your thumb back. And then you can go ahead and complete the table or the area chart by figuring out the area of each little section. So you get a sense that only 7.5% of people can bend their thumb but not roll their tongue, etc. So, and all 4 of those probabilities better add up to 1. So here are detailed directions on how you do an area model, just to step it out and spell it out for you. I'm not going to read through it, but it's available in your PowerPoint as you go to tackle the homework problems. Here's another problem. Okay, it says, in the U.S., 45% of people have type O blood, 40% have type A, 11% type B, and 4% have type AB. So it says Zoe and Dylan are friends, but they're not related, so they're not going to have any kind of consistent bloodline of blood type. What is the probability that they have the same blood type? Okay, so you got on one side Dylan's blood type, and the other side you got Zoe's blood type. So let's go ahead and make an area diagram that would represent the different quantities or percentages that their blood types could be. So we'll start off with Zoe's, and we know about 4% is AB, and I'm trying to make it kind of to scale. 11% is B, 45% is O, and another 40% is type A. So that would be the breakdown for Zoe's blood type. And then for Dylan's, we kind of do the same thing, except on a horizontal axis sort of thing. So AB is going to be 4%, B is 0.11, O is 0.45, and then type A is going to be 40%. So you notice how I've kind of scaled the drawings down. Now the question asks, this is our sample space, this is all our different possibilities. The question says, what is the probability that they would have the same blood type? So they would both be AB, or they would both be B, or they would both be O, or they would both be A. So in this case, we're going to look at all of those, where they're each the same. So they're probably the same as the probability of both AB, probability of O and B. And by filling in those areas, we could then determine the total area that would represent that probability of having the same blood type. So we'd add them up. So we'd say 0.40 squared, 0.11 squared, plus 0.45 squared, plus 0.40 squared. And that square is just calculating the area of these particular squares. So 0.40 squared is just 0.40 times 0.40. That's the area of that square. And then when I add them up, I ended up with 38.38, or 38%. There's a 38% chance that 2 people would have the same blood type, or at least Zoe and Dylan, given these statistics. Okay, so here's a new one, and you want to try to come up with your own area table that would represent what's going on in this game. So it's called flip to spin or roll. So you start by flipping a coin. If you get heads, then you're going to spin a big wheel. And if you get tails, then you're going to roll a little cube. So this is a pretty complicated little game. So what you do is you break it up. You say, all right, you're going to have heads, or you're going to have tails. So half the time you're going to get heads, half the time you're going to get tails. If you get heads, okay, it says if you start by flipping a coin, if the heads comes up, then you're going to spin a big wheel. So you take that little rectangle that has the head space, and you're going to break it into proportions to show, well, of 10 equal sectors, 3 are red, 3 are blue, and 4 are yellow. So let's break our little heads section, okay, so this section right here, let's break it into 3 sections, a red one and a blue one and a yellow one. So we're going to call this 0.30 the red one, because 3/10 are red, 0.30 the blue one, and then 0.40 the yellow one. All right, so that's going to give you the probability of rolling like a heads and getting a red. Okay, so now let's go down to the tails. Tails is a little bit different, because if you tails, then you're going to roll a cube. And in your little cube, your dice has 3 sides that are red, 2 sides that are yellow, 1 that's blue. So now we need to break up our tails little area section, this section right here. We're going to break it up into 6 compartments or portions, right? So we're going to have the if it shows tail, you roll a cube with 3 sides red. So in other words, half the time you're going to get red. Okay, so that 5 is red, and then 2 of the remaining times you're going to get yellow, and then 1 you're going to get blue. So 33% of the time, okay, so that would be 2 out of 6 different cube rolls is going to give you yellow. And then there's only 1 blue side, so only 1 out of 6 little sides of the dice is going to give you blue. And so the question says, if your spin lands on blue, or the blue side of the cube, what is the probability of winning a prize? So you have to calculate what's the probability of getting blue, either heads and then the blue spinner, or tails and then the blue cube. So you take those two areas and you add them up. The area of blue is going to be 0.5 times 0.30, which is 0.15, plus 0.5 times 0.17, which is 0.235. So there's your total probability of winning the game. 23.5% of the time you should win. Okay, and here's the last idea. This is just kind of introducing what it could look like. This is called a two-way probability table. And you see it's a two-way table because it's considering 2 different questions. The first question is kids who play, you're talking about how many kids play water polo versus how many kids don't. And so that data I've circled at the bottom represents, 52 kids play water polo, 98 kids don't, which is a total of 150 kids. So you'd take 52 divided by 150, or about 1/3 of the kids play water polo. In this case, I don't think this is a Merrimani data. This is just random data. So, and then you can consider another question, which is, what about kids who are on the swim team or kids who aren't? In that case, you're going to look at this column right here. Oop, let me back up. Sorry. You're going to look, oh, not that far back. You're going to look at this column right here, and you're going to say, all right, you have 28 kids in the swim team, 24 who aren't, a total of 52 kids. Oops, I did the wrong thing. I'm sorry. That's not what I want to look at. I want to look at this. Sorry. Kids who are on the swim team or not. So 61 kids are on the swim team, 89 kids are not. So if you want to know what percentage of kids are on the swim team, you'd say 61 over 150. And then the final question, so you got 2 different questions going on, about water polo and about swimming on the swim team. But then you can get a third question, which is called a conditional probability, which is, if you meet one condition, how does that affect the other one? So you say, let's say, for example, that you are on the swim team. Okay? If you are on the swim team, are you more likely to play water polo? So in that case, you're going to look at this data right here. You're on the swim team. Are you more or less likely to play water polo? So 28 out of 61 people versus 33 out of 61. So if you look at a conditional, the condition is you're on the swim team. Then you say, well, are you more or less likely to be playing water polo? Okay, and we're going to be looking at these kind of data tables and figuring out, does it make a difference if you're in the swim team? Are you more likely to play water polo if you are swimming versus not swimming? And we will study those to try to understand these conditional probabilities and if they're dependent or independent. In other words, is there any kind of relationship between being on the swim team and playing water polo? I would argue here at Merrimani that there definitely is. You're much more likely to play water polo if you're also on the swim team. But this data may not play that out. Okay, so we're going to consider more detail of how to look at those in the coming days, but for now, at least you can see this is a two-way probability table, some way of modeling probabilities and thinking about different questions. Okay, that concludes our lecture for today.